Evening and welcome to your next lesson on foundation level mathematics, algebra. So this time we're looking at types of equations. So we've looked at before what an equation is and how to solve them and things like that. But then we've got different types of equations that we might use in different contexts, and they have slightly different meanings. So we're going to take a look at that today, how to work with them, what they mean. So we've got uh, identities first, which is the type of equation which we often use for rewriting things in say a useful form. Little commonly used ways of forming things that we want to remember. We have formulae. We've seen some examples of that before, which shows like a relationship between multiple variables, and perhaps we want to rearrange those formulae to you know change which variable we want to focus on. Well, proportionality. So we've seen this before, just with numbers. We're looking at it now in algebra. So when we have a proportionality, how can we then form an equation from that proportionality? And then finally, functions, which is another way of showing an equation specifically in terms of input, output. When we put an input into this equation, what is the output? And why do we use this way of for expressing an equation? What are the uses of that? So let's start off with identities first. So what an identity is an equation that is always true for all values. It's not like an equation where like a general equation that we're trying to solve. It's something that's always true, and we can use that to then rearrange an equation into perhaps a more useful form. Like if you actually tried to rearrange this to solve a to try and solve the identity like the way with a normal equation, it would just come out to something like 0 = 0. It'd be pointless because it doesn't actually carry any information. We can use them to help simplify equations or change them into a different form. That's like the main use that we use them for. So here's one example, which is shows the relationship when you've got like two variables here, like the difference between the square of two variables, like a and b. We can factorize it into this form, or vice versa. If we have something factorized in this way, it's essentially the same as the difference between the square of those two variables. And you might want to try, you can always pause here and try and expand out those brackets. You'll find it will come out to a squared minus b squared, and so you could cancel out both sides, and it would essentially come to 0 = 0. So it wouldn't be meaningful to try and solve it. It's just showing how we can change the form of something, and this is a really useful identity that we might come across a lot. Like say with a quadratic, for example, where you might have something of the form like x squared minus 64 and equals 0, and that's an equation we're trying to solve. And it might not be in your familiar form because that we're used to, because you normally have three terms, don't you? An x squared term, an x term, and then a constant term. But you got x squared minus 64. But you might notice that that's basically that same thing as x squared minus 8 squared. In which case, we could use this identity, and you'll see that if we factorize it, it would be x plus 8 times by x minus 8. That's a common way we might use this, and then you could solve that quadratic in the usual way. So that's a good example of an identity there. Here's another couple of examples showing what's known as a distributive property. This is something to be very aware of. Like what we've seen before when expanding a bracket. Like here we've got a times by b plus c inside a bracket, and you see the a times the b, and you get plus a times the c. That's showing how multiplication can distribute over addition. And the one below, we've got a similar thing where you see a power can distribute over multiplication. So you've got x times y multiplying each other. And if you take that to a power n, it's the same thing as doing x to the power n times by y to the power n. You see that power, we can do the power of each one individually. And that's something what's known as the distributive rule. You don't need to necessarily know that term. What you do need to know is that it only applies in these ways where multiplication or division can distribute over addition and subtraction. Powers and roots can distribute over multiplication and division, but powers and roots won't distribute over addition or subtraction. So if you had x plus y in brackets and then took that to the power of n, say, that wouldn't be the same thing as x to the power n plus y to the power n. So that's an important thing to know. So yeah, here's a couple of like identities sort of showing that result. Another common identity is this using trigonometric functions. Now, you may or may not have seen trigonometric functions yet. We haven't covered that yet in this course. We'll be doing that later when we look at trigonometry. But I have three trigonometric functions here: sine, cos, and tan, and we have this identity that relates the three of them, which is a really important one as well. So these are all identities you kind of need to be aware of, showing the relationships between different variables. But like I was saying, they don't carry information. It's not something you solve. It's more just showing you a way of rearranging things. So that's what an identity is. Next up is formulae. So what is a formula? A formula is an equation that expresses a specific relationship between two or more variables. So typically you'll have one uh, variable or unknown quantity, which is known as the subject of the equation. So you might have something where it's like x equals, and then something going on the right side with other unknowns. And so it's kind of then telling you based on those other unknowns, how do you then calculate what the value of x is, say, or anything. We're going to look at a few examples in a second. So they're not simply a rearrangement of terms like identity. Like it's something we would try and solve, but they provide like a rule of how one variable is related to other unknowns. And so it's if we know what those other values are, we can then use that formula to calculate what this the one that we're focusing on. We know how to calculate that one. Uh, and they're used in many applied math subjects such as physics, engineering, economics, but the list goes on. You'll encounter formulas well beyond mathematics, actual mathematics. So one example of a formula we have seen is the quadratic formula. So you see this here, we have x equals this big complicated expression. It shows the relationship between, like for a quadratic equation of ax squared plus bx plus c equals 0. So we've got a quadratic in that form. This formula then shows the relationship between the solutions to that quadratic, which is x, and the coefficients of the terms a, b, and c. And so that's one example of a formula. Another formula we've seen is something like this: density equals mass over volume. This formula shows how would you calculate density um, if you're given a mass or a volume. Excuse the typo there with volume. Um, so that's another example of a formula, and we could always then rearrange this. Like given a density and a mass, we could then find out what the volume is. We're going to take a little look at that in a second, how that works. We've got a couple examples here from geometry. Again, you might be familiar with these, you might not be. We haven't looked at geometry yet. You might notice the first one as Pythagoras' theorem. Uh, the second one is calculating the area of a circle. If you don't know, if you're not familiar with that yet, doesn't matter. We're going to cover that later. But at the moment, we're just looking at formula. So that first one, it shows a relationship between the sides of a triangle, where A, B, and C being the sides. This equation shows that relationship between them. And so, again, if we know what two of the sides are, we could find out the third using this formula, or the second one being the area of a circle, the area being A, R being the radius of that circle. If we know what the radius is, we could then find out the area. If we knew what the area was, we could then find the radius using this relationship. So that's the power of formulae. It shows relationships between different variables, and we can then rearrange them to find whichever variable we want. And so that's what we're going to look at right now. It's what's known as changing the subject of an equation. So, or changing the subject of a formula, I should say, in this case. So, say if we had something like this. So this is, like that Pythagoras theorem we just saw a second ago. Just I'll put it as C being the subject. So C, known as the hypotenuse. Again, if you don't know that word, it doesn't matter for now. Um, this is the formula for calculating that side. Say if instead we don't want C, we wanted to find out what B is, one of the other sides. How would we do that? We want to create a formula for B instead. Well, what we can do is we can essentially just use the skills we've already learned in solving an equation. Changing the subject of an equation is essentially the exact same thing as solving, but you're not going to get a numerical value. Like, because here we've got a formula with three unknowns, C, A, and B, and all we're doing is we're showing the relationships between them. So here at the moment, we've got C in terms of A and B. What that means is, like, in terms of A and B, it basically means you need to know A and B in order to calculate what C is, which we can see here. If we knew what A and B were, we could put that into this formula and calculate C. So now if we try and solve for B, we're not going to get a value. What we'll do is we'll get a different expression in terms of C and A. So let me show you how that works. So say, first of all, we want to try and get the B out of there. First of all, it's enclosed in that square root. So let's get rid of that. If we square both sides, we'll get C squared equals A squared plus B squared, same equation we saw a moment ago. Now, if we want to get the B squared by itself, we could subtract A squared away. So I've subtracted A squared from both sides here. So we've got C squared minus A squared on the left, B squared on the right. But now I've just kind of swapped it around just so that we've got B squared on the left. We generally, the variable we're focusing on, we want to get that on the left. And now, finally, if we want to know what B is, because we've got B squared at the moment, we don't want B squared, we want B. If we square root both sides, that will cancel out the square on the B. So we'll just be left with B, which is what we want. On the right-hand side, we're now square rooting what's there. And you see, we get the square root of C squared minus A squared. And we're all done there. And that distributive property that I was talking about earlier, you can see we're kind of, in a way, using it here in the sense that we're not using it. Like, square root in C squared minus A squared is not going to be the same thing as C minus A. Like, you can't square root each one individually. So you see that, like, this would be the answer here. So now we've got B in terms of C and A. Now you might want to pause here and try doing the same thing again. Try to get A in terms of B and C. And you find it will be a very similar formula because it's A, B, and C all kind of the same there. Like they're all just by themselves being squared. But yeah, a good little practice there. Let's take a look at a different one, which is this little formula here, which is a formula from something known as kinematics, which you probably not done before. It relates, things like velocity and acceleration of like a moving object. If you do physics at GCSE or certainly A level, you'll probably encounter this. So here we've got a little formula here relative to other unknowns, U, A, and T, where A, like I mentioned, is acceleration. Say if we wanted to rearrange this to make A, that acceleration, the subject of the equation, because at the moment V is the subject. So when you've got something like this, where V equals something of other variables, V is the subject. It's like the thing we're essentially focusing on. We want to change it to now make A the subject. So we want to get this into the form of A equals something doing with other variables, whatever's going on over that side. Okay, what do we do? So say if we subtract U from both sides, first of all, so that will leave us with, V minus U equals AT. Again, I've kind of just swapped the equation around to get the A on the left-hand side, essentially the same thing though, isn't it? So we've now got A times T equals V minus U. Well, if we want to just get A by itself, well, let's divide both sides by T. So the T will cancel out on the left-hand side. And now we've got V minus U divided by T. And so that would now be the formula for A in terms of the other variables. So, okay, I'm hoping this makes sense. So let's look at a little one like this. So this isn't any actual formula. This is just something made up with different variables like this, X and Y. But you see how we've got multiple occurrences of the Y. So say if we wanted to make Y the subject, what we need to do for, like, if we want to get it in the form Y equals something in terms of X, we need to bring those Y's together first, because at the moment we've got two occurrences of that Y. So we can bring them both to the same side by, say, if we subtract Y from both sides. And you see I've added 3 to both sides as well to cancel out that minus 3 on the left. So I'm kind of doing 2 steps in one there. If that is not clear what I've done, you might want to pause here and sort of do those 2 steps individually. So I'm minusing Y from both sides, and then I add 3 to both sides, and it will get this. And now you see those two y's we can bring together into 2y. In more complicated scenarios, you might have to use factorization. So if you go back to our previous lesson where we was looking at factorization, you might notice a thing that happens if you have multiple occurrences of a variable like that, and then you factorize it out. It can then it basically you just then got that one occurrence times by some stuff in brackets, and then that thing in brackets you could always just divide away, say onto the other side of the equation. If you divide both sides by that bracket, it will cancel out on that left on that side that we don't want it. So, but that's something you're not so likely to encounter. You might just get something more like this, and then finally we can divide both sides by 2. So okay, so here's some examples of changing the subject, which I've noticed sometimes can be a little bit tricky for people. But the key thing to remember is it's basically doing the exact same thing as solving an equation, but you're just solving it not to get like an actual numerical value. You're going to get the answer to what you're trying to solve in terms of other variables like this. So I'm hoping that makes sense. So let's now look at proportionality. So we've already done a good some good work on this in our section on ratio and proportionality. So we have a direct proportionality, which is something like this. When we say one variable is directly proportional to another, and you see that we get this little squiggly symbol between them, this is the symbol which represents proportionality. So this is basically saying y is proportional to x. And so this is what a direct proportionality is. And it's basically saying as one variable goes up, the other one also goes up. So the simplest case of a direct proportionality would be just, as an equation, would be just y equals x. So if x goes up by 1, y goes up by 1. If x goes up by 2, then y goes up by 2, and so on and so forth. If x goes down by 3, y will go down by 3. But in general, we don't have that. We'd have something more like this. So you might recognize this as essentially a linear equation because we've just got y equals some equation in terms of x, just a very simple one, x times by some unknown constant, but there's no powers of it. It's not x squared or anything like that. So it's just like a linear equation, but we don't know exactly how that relationship is at the moment. So we know it's a linear one, but so it's just a very sort of straight, um, like if you think of it like a graph, if you've looked at graphs yet, it's like a straight line, and then that k is determining then how steep is that, how steep is that relationship between the two. So that's the key step to then go from a proportionality to an actual equation. It's basically going to be the same thing, except it's going to get multiplied by that unknown constant like that. And then if we want to actually know what that unknown constant is, so I guess it's a good time to explain the difference. I've used these terms constant and variable, exactly what that is. You have y and x are like our variables. So it's showing the relationships between these two variables, and these two unknown values, and they can change. Like x can change, and then this equation then tells us how y will change as x changes. So they're variables, they vary, they have many different values they can take, whereas k is a constant. So it's an unknown value, but it's just one specific unknown value. It's not something that's varying. So that's the difference. A variable varies, a constant doesn't. So we're trying to find out what that is. And in order to find that out, we need something what's known as a constraint or a boundary condition. Um, and that would look something like this. Basically, we need to know a particular uh, point. Like if you think of it as a graph, it would be like knowing a particular point, or it could be something like this, where basically you need to know what is the value of y for a particular value of x. So they're varying, aren't they? X and y. And this equation describes how they vary relative to one another. All we need to know is a specific point. What is y for a particular value of x? And that's what we've been given here. Because if we have that, we can substitute those values into this expression, this equation we have, and it will give us a little equation of k that we can then solve. So see, it'd be something like this. If I put in y equals 6 and I put x equals 2, you can see y is then equal to 2k, or k times by 2, which is just 2k. And so that is something we can easily solve, can't we? And we find k is 3. And so the equation is y equals 3x. So okay, overall we've got a proportionality that allows us to form this equation, essentially the same thing, except the our right hand side is getting multiplied by some unknown constant. Then we need some kind of boundary condition to find out what that constant is. That constant tells us then sort of how steep or how strong that proportionality is between the two variables. Right, so I'm hoping that makes sense. Let's move on to other types of proportionality. So we've got the inverse proportionality with something like this. Remember when we take the reciprocal. So this is like when two variables are, well, they're inverse to one another. So as one goes up, the other one goes down. And if this one goes down, the other one goes up, and so on, as opposed to direct proportionality where they go up and down together. Um, so as a proportionality, it looks like this. If we wanted to write that as equation, we know it's basically the same thing, but that right hand side is getting multiplied by some unknown constant. And it works in very much the same way. If we want to then know what that actual equation is, we then need a boundary condition like this. And we can substitute in those values, and you're going to get a slightly different equation, but we just solve it, using our techniques that we know. So here, if we times both sides by 4, we'll get k equals 20. And so we can put that in, and we can see this is then going to be our equation between the two variables. So this is a really useful thing, because sometimes in real world situations, we might know the proportionality between two things. We might generally know sort of as one grows, how does the other one go? Does it go up, or does it go down? We know the general sort of relationship between them two, but we don't know specifically sort of how strong that is. And so that's why we do this. You bring in that unknown constant, which determines the strength of that proportionality. And then if we know a specific piece of information, this constraint, this boundary condition thing, we can then find out what that unknown constant is, and then we get an actual equation as opposed to just a proportionality. So that's the usefulness of this. Um, let's look at a couple more complicated scenarios. So say if we had something like, if p is proportional to q squared, that would look something like this if we write it as a proportionality. And so if we put it as an equation, it's the same thing. It's going to be the same thing, but just you're getting multiplied by that unknown constant. Again, we might be given we'd need some kind of piece of information in order to then fix that constant. So we need to know a point. What does p equal to for a particular value of q? And we can substitute that in. We get a little expression for k, and we can solve for k. And then we can put that back into our actual equation that we had. So if we know now k is 36 over 9, then yeah, p is equal to 4q squared. Another example here, if we have m is inversely proportional to the square root of n. So sometimes you'll get questions like this, and it's put in words, and you need to then be able to put it into an actual equation, or in this case, like a proportionality, like this. M is proportional to 1 over root n. So if it's inversely proportional, we know it's going to be like a reciprocal like this, 1 over root n. And as an equation, okay, so we know it's going to be the same thing, but multiplied by some unknown constant that sets the scale. We have some kind of boundary condition. We can then substitute that in. So we've got 3 equals k over 7. If we times both sides by, because it's the square root of n on the denominator there, isn't it? So we get the square root of 49, which is 7, or potentially minus 7. So k could be technically, plus or minus 21. And so then if we put that back into the original equation, it'd be like m equals plus or minus 21 over n. It depends on the context of the question if they need you to take into account both roots. Right, but that's a more complicated one. You're less likely to come across that foundation level. But you see, it's very much the same thing. One more challenging example you might get is something like this, where we might be given a proportional to b and b proportional to some other variable c. So here, a is proportional to b squared and b is proportional to the cube of c. And then we're given a boundary condition of a and c. We want to find then an equation for a in terms of c. So, okay, right, let's get that information down as actual mathematics. So if a is proportional to b squared and b is proportional to c cubed, then we know we can form these equations, don't we? Like a is equal to some constant times b squared, b is equal to some constant times c cubed. And then what we can do is we can do a substitution. So we'll look at this a bit more when it comes to something known as simultaneous equations in a later lesson. And so you see here how we've got b is equal to jc cubed. Well, we can take that and substitute that into the first equation where we have b squared, put the jc cubed in there instead, because we know b is equal to that. And so now we get this little expression, this equation, sorry, and we can then use our indices laws to expand out that bracket, where we're taking the square, essentially using that distributive property that I mentioned earlier. We've got j times c cubed, and we're taking that to a power 2. Well, we can just apply that power 2 to each of the uh, like the j and the c cubed. So j becomes j squared. C cubed is going to become c to the power 6. Using our indices laws, 3 times 2 gets 6. Now, what do we do in this scenario? So we've basically got a equals c to the power 6 times by some unknown constants, k times j squared. But k and j are both just unknown constants, and so together it's just another unknown constant. So we could put that together into just some other unknown constant, capital K. And you see the proportionality here between a and c. That's what we really need. And now we can just solve this in the same way we've done before, because if you're given a boundary condition, a is equal to 9 when c is equal to 1. So if we put that in, so 9 is equal to k times by 1 to the power 6, we can see k is equal to 9. And so a is therefore equal to 9 times by c to the power 6. So this is a really useful thing we can do as well. Like if we've got a proportionally, we know what a is proportional to b, and we know what b is proportional to c. We can combine those together to then find out what a is proportional to c. And this is the way we do it. And yeah, of course, we need that boundary condition in order to find the actual equation. So yeah, quite a tricky problem. This is about as advanced as it can get really for you guys that when it comes to proportionality with algebra. So let's move on to our final thing. One quick final thing: functions. So what is a function? How do we use them? So we don't do too much on functions at foundation math. We just need to know what they are and how to use them. So a function is a good way to think of it is like a machine, and it's like it takes an input and then it spits out an output, and that input sometimes is what's referred to as an argument. It's kind of a strange word. There's like a historical reason for that. You might want to look up. The argument is basically the input into this function, and then that function does a series of operations to produce then an output. Each possible input to the function has exactly one output, although multiple inputs can produce the same output. So that's an important thing with a function. One input produces one output, but it doesn't necessarily go the other way around. Functions provide a compact notation that allows us to break down complicated operations into concise modules. So say it's like say if you've got a series of operations that maybe you're doing over and over again, you can compact it down into this function. That function does those series of operations, and so whenever you then use that function, it's basically doing all those operations for you. So that's what it's often used for. So let's take an example. Like say if you had this. This is our notation for a function. So f being a function, f of x is how you would say this. F of x equals 2x plus 1. And the key thing is f is a function, not a variable. And so when it was, if you had a variable like f with x in brackets like that would be like f multiplied by x, isn't it? But this is not the same thing. F is a function, and what we're doing is we're taking x, and that x is our input to the function, and the output is 2x plus 1, basically 2 times x plus 1. So we could write it like this, like a machine, like x is going in as an input, and now f is doing a series of operations to that input. What it's doing is it's multiplying it by 2, and it adds 1, and then it produces the output f of x, or sometimes the output we would label y. And then you'd have basically y equals f of x. That you might see that notation. That's basically what that means. y is just the output of that function. So this would be an example of a function as well. Like you can have non-linear functions like this, and you see for each value of x we put in, we're just going to get one possible answer, one output. Whereas you take something like this would not be a function because we know from square roots it gets two possible answers, doesn't it? If I do the square root of 4, it gets me plus or minus 2. And we know functions only can have one output. So this wouldn't be a function, this a valid function, unless we restricted our potential answers. Like say if we only allow positive outputs, okay, then it perhaps would be acceptable. Um, but you don't really do anything like that. So generally, you're just going to get linear or quadratic functions, and we just need to know how to use it. So say if you had a quadratic function like this, you might want to find what is f of 3. That's what a question might ask. What is f of 3? That's basically saying if I put 3 as input to this function, what is going to be the output? And we can calculate that by just putting in 3 into that equation. So it's stuff we've already done. It's just a different way of kind of wording things, and there's reasons for why we use this. If we want like I was saying, this more compact notation, certain series of operations that you might be doing over and over again, you can put into it, like, make it a function. And when you move, working with more complicated equations, the use of functions can be really handy to make things neater. Um, so yeah, we put in that value of 3. So you see we get 3 squared plus 4 times 3 minus 12. You work that out, you're going to get 9. So 9 would be the output. Or vice versa, you might be given something like this: solve f of x equals 0. Okay, well, what does that mean? We're basically saying, okay, f of x is the output. We're trying to find when is that 0. So we're basically trying to find out when does this function produce an output of 0. And that's going to be basically, okay, when this quadratic is equal to 0, because that's what the function equals. And so we can then just use our techniques that we've already learned before to find what those solutions are. And we get two solutions: x equals minus 6 or x equals 2, which is fine. Because remember, we're only, each input can only produce one output, but an output can have multiple inputs that produce that output. So here we've got an output of 0. We've got two inputs, x equals minus 6 and x equals 2, that both produce an output of 0. That's fine. It can go that way, just not the other way. So that's functions. And we just need to know how to use them, and like this. Find, given an input, find an output, or given an output, find the input, or to plot them, for example, which is something we'll look at later. So there we go. Let's leave that there. Learned a lot there today about different types of equations. Here's a little did you know about functions for anyone who's interested in computer programming, writing code and things like that. Functions play a very important role because we might have something very complicated that does that produces that does a particular task basically, and given certain inputs it will just produce outputs. And so this whole big complicated set of operations we can then put into just a single line, which is really nice. This is what makes it so much easier. Certainly if we're going to use it over and over again, we can take complex problems, break them down into smaller ones. So if there's particular operations, like I was saying, that have to be done over and over again, you can just then invoke that function over and over again rather than writing out the whole series of operations. Um, and yeah, it allows things to be very predictable because it only depends on its input and it will produce an output. It and it's always going to work the same way. Whereas imagine if you was trying to work things out over and over again, it'd be easy to make errors and things like that. Whereas if you just got one series of operations that you've written once, it's just there and it's going to stay the same each time. Um, yeah, and when computers are very good for doing iterations where we doing the same thing over and over again for like many different inputs. Functions are then really useful for that. So we will take uh, a little look at iterations at some point, but not um, very much. It's basically when you're repeating something over and over again. Functions can then be very good in conjunction with that. So here are our takeaways for today's lesson. So next time we're going to be moving on to plots. So I mentioned that a moment earlier, where we have, say, equations, this relationship between different variables, and we want to represent that as a graph, like a drawing that allows us to look back and see the overall relationship between those variables as like an illustration, a picture. So we're going to look at how that works next time and how we use those. All right, so I will see you there.